Good afternoon, everybody, and welcome to the Doctoral Academy this afternoon. This afternoon, Professor Richard Heft is going to be speaking to us about how to present our statistics in a paper. So I'm going to hand over to you, Richard. Thank you.
Thank you very much, everybody. Nice to be back with you. Today's topic is something I know that troubles a lot of people, and it's also very important. But the problem is it's extremely dry to give a lecture on, and I do apologize for that. I think the trick here is not to attempt to take away the detail of what I'm going to say. It's take away the principles behind what I'm saying. I am busy producing a document, that summarizes the important bits of what I say, and that we will certainly make available to everybody. So please, if you're not very good at stats, in fact, you may find that I leave you behind very quickly. Well, just relax, have some coffee or something, and just get the idea that there is some sense to the way in which we are required to write when we write our papers or write our dissertations and report our results. So today will also very definitely be far more relevant to those who do the sort of research that results in numbers than those who do pure qualitative research. Anyway, we'll get straight into it, and I'll start by sharing my PowerPoint. Right, there it is. Go back to the beginning. The title is self-explanatory. Right. Now, the first thing is your methods. I find that when people ask me to have a look at their papers or their theses, whatever it is, often the statistical section of the methods is not only wrong, it's often completely wrong, completely confused, shows a complete and utter failure of any understanding of what actually happened to their data. It's quite clearly, just a sort of regurgitation of something half remembered that the statisticians said, coupled with a couple of nice sounding phrases that you remember from other people's papers. Well, if you've got a discerning reviewer or examiner, that's going to be an absolute red rag or red light, however you want to see it, for them. I'm going to be mentioning that how you handle your data statistically is as important as how you obtain your data in the course of your study. It can make or break your conclusions. And therefore, it's absolutely essential that you know what you've done. Even if you're not a statistics fundi, you've got to more or less understand what has been done to your data. And secondly, in your methods section, you've got to describe it in such a way that somebody seeking to reproduce your results can also reproduce the statistical testing in order to come up with the same result as you. I'll make a comment on that in my second to last slide. Right. Now, here's the first thing. All the recommendations I'm giving you come from a large publication from the International Committee of Journals International Committee of Editors of Medical Journals. All right, so they sat down and had a long session and came up with guidelines, uniform guidelines for people submitting articles to medical journals. So this is largely based on that, plus on a paper expanding on that by Altman, which I'll reference a little bit later. So these are actual recommendations from the editors of medical journals. And the first one is they want to know what statistical software you used, where it comes from, and what version you are using. Okay, now you may wonder why. Well, apart from, I suppose, giving credit to that particular company, if you know any stats, you'll know that there are often different ways of obtaining a particular statistical result, and they may give slightly different values. So it could be important to a reader, a discerning reader, to know exactly what software you used. A discerning reader, statistician, may, for example, know that there was a bug in version 15.1 of 2019 that was subsequently sorted out in version 16 of 2020. And that's useful information to that reader. It might help him to understand why it is that a certain result did not work out as expected. So the first step is, this is required, and this means you've got to do a little bit of work. If you're doing Excel or something like that yourself, then you just need to go and do a Google search and find out the actual name of the software and the publisher and where they are based. College Station is a town in Texas. Okay, and you're going to have to look at probably the help menu, whatever it is, the options of your software to see which version you're using. And if you change versions, then you're going to have to update that. So that's the first step. The second thing all editors state is critically important. Okay, you have to say what level of significance we are accepting. And more or less uniformly for biomedical journals, it is 0.05, but not necessarily. And certainly if you're working in other sciences, 0.1 may be acceptable in some psychology sciences, and in physics, 0.00001 may be required in order to regard something as significant. So it's essential somewhere that you state your level of significance. You've got two ways of doing it. One is to say a p-value of 0.05 was regarded as significant. Or if you fancy and you understand a little bit of what you're doing, you might say an alpha level of 0.05 was considered significant. If you don't know what alpha error is, it really is important that you find out. Alpha error is the probability, in other words, the risk you as a researcher take that you will mistake random differences in your data, which results from chance effects and sampling, as I've talked about before, for real differences. So if I take two totally unrelated things and measure them often enough, sooner or later, something that looks like a real association between the two will come out. And we set it that we don't want that to happen more often than 1 in 20, 0.05, 5%, and that is our alpha error. So we need to state an alpha level. Good. Now the next thing is we are obviously going to describe results, might be ages or CRP values or mortality, whatever it is. And you need to explain in your methodology how you describe your results. Okay, this is usually in terms of what's called central tendency, the midpoint of your results, and the distribution. Fancy words for things that you know very well. For example, you may state, results are reported as mean, open parenthesis, standard deviation, close parenthesis, for normally distributed data. Then you've told people up front how you're reporting your data. And secondly, you're telling them the format in which you're reporting it, so that when they come across results in that format, they'll know what you are talking about. Okay, and the parenthesis is now the preferred method of showing a standard deviation. The old plus minus is no longer recommended, and you should really not be using it. Use mean, open parenthesis, standard deviation, close parenthesis. Once you've identified it as such like that, then you don't have to put SD or standard deviation inside the brackets along with your numbers. You've defined it already. Okay, so for normally distributed data, mean and standard deviation are recommended and expected by journals. If your results are skewed, then you should rather report them as median and interquartile range, which we talk about in the statistics talks, but I'll show it to you very briefly. It's best to keep away from words like parametric and non-parametric. They do have peculiar implications and meanings which are not really what we mean when we talk about distributions. Okay, we should talk about parametric tests, but normal distributions, non-parametric tests, but skewed distributions. Right. And of course, you might want to combine both of those in your paper. Results are reported as mean, open parenthesis, standard deviation, close parenthesis, for normally distributed data, and median, open square bracket, interquartile range, close square bracket, for skewed data. Goes without saying, of course, that if you don't have any skewed data with medians and interquartile ranges, then you don't put that line in your methods. That should be fairly obvious, but often isn't. So, just to stress again, firstly, this line in your methods tells your readers how your data are handled. They'll be looking out for means and standard deviations or medians and interquartile ranges. And secondly, it serves as the key to the reporting data in the text. So if, for example, in the top line, there is a result you've written, it's not necessary to say which one is the standard deviation because you've effectively defined it in your methods. Anything that looks like a normal distribution that has a number with a open parenthesis and a number and another closing parenthesis, that is a standard deviation. And similarly, at the bottom, medians followed by square brackets means that inside the square brackets is your interquartile range. That's your 25th percentile up to your 75th percentile. Okay. The point I'm making with this slide, right, is you don't always have to talk about results generically. If, for example, there's only one thing you're measuring in your paper, then in your methods, you could just go straight on and say the median plasma protoporphyrin concentration, plasma protoporphyrin concentrations are reported as median and interquartile range. If, on the other hand, there are lots of different things that you're going to report on, then it makes sense to cover them, all of them, as a class with that first sentence. Okay, so another point is that sometimes the range is also used for skew data. That's the range from minimum to maximum. As in this example, the median plasma protoporphyrin concentration was 80. That's your central tendency. 20 to 600 is the middle 50%, the interquartile range. Range 5 to 1200, minimum to maximum nanomoles per liter. That might be useful information in terms of people understanding and being able to visualize your results. So it's really up to you, and depending on circumstances, where you decide whether you decide to include the range as well as the interquartile range. If you do include range, then put the word there as well. That's not normally described in the methods. The other thing just to notice here is that we've put the units right at the end because they apply to the 80 and the 20 and the 600 and the 5 and the 1200. So effectively, we've moved the units right to the end, so it covers all of them. We don't have to say 80 nanomoles per liter, brackets 20 nanomoles per liter to 600 nanomoles per liter, etc. We can put it once. I prefer to have it at the end rather than next to the 80, because as I said, it really does apply to all the other numbers as well. Right. Now, the point I want to make here, none of this is going to make sense if you don't have a clear idea of what it is that you're describing when you talk about means and standard deviations or interquartile ranges. You've got as little right to write in your methods how you used those things when you really didn't understand them, as you have to write in your methods about your actual experimental design when you didn't actually understand it. You need to understand what it is that you're writing. Otherwise, you really do end up with the sort of rubbish that I talked about earlier that is very, very embarrassing and really ought to raise serious concerns in a reviewer or an examiner. So the little method section of the statistics is not, a statistics section of the methods is not an afterthought. It's actually quite critical to what you're doing and offers very quick and easy insight to the reviewer or examiner as to whether the author or candidate actually knows what they're talking about. So if we say the mean plasma sodium concentration was 140 with a standard deviation of 2, then you must have a very clear eye in your mind that this is all you're saying. The mean was 140. One standard deviation was 2. 2 standard deviations is 4 and covers 97% of all your values. And it's symmetrical because it's normally distributed. So that's the mental picture you must have in your mind if you're going to go writing in your methods about using means and standard deviations. They're not just mysterious numbers that fall out of the sky. They mean something. And similarly, if you're going to talk about skewed data in terms of interquartile ranges, medians, and ranges, you need to have that picture on the right, that this is skewed. The median is sitting to one side, half the values above it, half below it. The box outlines the first and third quartiles, 25th and 75th percentiles, hence the word interquartile range. And the range maps out the minimum value and the maximum value. So once again, if you don't even have a clear idea of what that is, then you can hardly talk to people about how you're quoting results in terms of medians and interquartile ranges. Right, so that's a little bit of introduction, really. Now, when we talk about reporting actual statistical tests, one of the first ones that we're often going to do is comparing groups. Are males older than females? Did the control rats have a higher adrenaline level than the test rats, etc., etc.? So again, you've got to have this mental concept of what you're doing when you do a test. If we are going to compare two groups with normal distributions, as shown there, there are two means, two lots of standard deviations and 2 times standard deviations, and we want to know if those means are significantly different. A light should come on, a bell rings, and you know that is student's t-test. So again, if you're going to write in your methods that you use student's t-test, you can't do that if you've got no idea of what student's t-test is used for and when it's appropriate. Now, you don't even have to know how to do a student's t-test, but you can't write it up in your methods if it's, you know, like speaking Martian or Russian or something to you. You're just asking to be caught out by your reviewer or examiner. And you need to know that if you've got more than 2 groups, then we use a test called analysis of variance. You probably better know why it's usually referred to as one-way ANOVA 2, just in case you ever have a case to do a 2-way ANOVA. Right. And you need to know that if your data were skewed, then the t-test would not have been appropriate. And you would probably have done a test like the Mann-Whitney U-test, and that only works for 2 groups. If you have a 3rd group, then you use a variation called the Kruskal-Wallis test. So immediately you see we can relate test to whether the data are normal or skewed, and we can relate test to whether there are 2 groups or more than 2 groups. So if you go gargling and jumbling and mushing this all up when you write your methods, it will be immediately apparent to a reviewer or an examiner. And for me, the danger is not that they say, oh, this person doesn't know statistics, or, that's not the end of the world not to know statistics. The worry is that they will say, this person doesn't actually know what they are doing when they try and analyze your data. How can you believe the conclusions drawn by anybody who didn't actually know what they're doing? They couldn't even describe it, what they did accurately, let alone do it accurately. So that's the point I'm making here. This is not a statistics test, a lesson in disguise. It's making this point. Right. So these are phrases that you might want to put in your methods. Again, of course, let me make the point that there is no absolutely right text to use and other text is wrong, but these are things that work. But the bottom line is they are simple English, right? So it's quite clear that was what was done. It's not some mysterious religious formula, okay? It says, mean values were compared with a two-tailed unpaired student's t-test. Now, it may take you a little while to learn what a two-tailed unpaired student's t-test is, but that statement is a simple, straightforward, factual statement. Mean values were compared with a two-tailed unpaired student's t-test. In other words, that's what you or your statistician did. It's not some magic formula to be dropped in your methods to make them look good. Similarly, mean values were compared with a two-tailed student's t-test for paired samples. Okay, it says exactly what was done. And if that's what was done, then that's what you write in your methods. If that's not what was done, then you should not be writing that in your methods. So if you don't actually know what has been done, then you can't write up your statistical methods in your methods section. You've got to know it. Right. Here's a more complicated one. Mean values were compared by one-way ANOVA, and the means of individual factors were compared post hoc with the two-T-Kramer test. Again, the terms may not be all that familiar to you, but it's a very simple, straightforward, unambiguous English statement that says what happened to your values. So you've got to know what was done to your values, and preferably have some understanding of what happened, even if you can't do the test yourself. Okay, you've got to have an idea of that ANOVA, testing the means of more than two groups. Otherwise, it's going to be perfectly obvious when you write up the methods that it was a sort of fruit salad of sentences that have something to do with statistics thrown together, which is what I've seen all too often. Right. So just to summarize that, you do need to know what stats your data require. You can't farm out the analysis of your results to some statistician and then just accept what they say and write it down word for word without understanding what on earth has happened. Okay, you do need to have some understanding, and you do need to get them to explain to you what they've done, even if you are not capable of actually doing it yourself. There needs to be some understanding. Right. So when we compare groups, we will have statements in our methods such as this. Median values were compared using a Mann-Whitney U-test. Again, sorry, there shouldn't be an H in Whitney. Exactly the same point, a simple, straightforward English statement. It had better be correct. Okay. If you didn't use a Mann-Whitney U-test and it becomes apparent to the examiner or the reviewer, well then quite correctly, they're going to have questions. If you write some nonsense, like mean values were compared using a Mann-Whitney U-test, then again, assuming it's not just a typo, you've given away your ignorance, that you don't actually know what you're doing with your results. And there's a more complicated example at the bottom. But again, all I'm begging you to do is when you write the section, make sure you understand what you are writing and that it is the right stuff. It is not magic formula to be sort of sprinkled over your method section, like icing on a cake. It's a straightforward statement of what was done. Okay. Control rats were given 50 milliliters of gabapentin solution. At 4 hours, their adrenaline levels were measured. That is straightforward statements of what you did to your mice in your methods. Median values were compared using a Mann-Whitney U-test. It's the same. It's a straightforward statement of what you did with those adrenaline values that you got from your test and control mice. Right. And again, as I said, there's no right or wrong way to write them as long as they make sense. So here we might have decided to combine both. If we've got both skewed and normally distributed data, then instead of making 2 sentences, we've run it together into 1 sentence. And if you've understood a little bit about the statistical reasoning behind what I've said, that sentence will make perfect sense to you. Right. The only point I'm making here is one I made a little bit earlier, actually out of sequence. Right. It's perfectly acceptable in your methods to actually use the names, of what was compared. Instead of saying mean values were compared by one way ANOVA, you could say the mean hemoglobin concentrations in patients drawn from the eThekwini, Ilembe, and Utukela health districts were compared by one way ANOVA. On the other hand, if you're doing 5 or 6 or 8 one-way ANOVAs in your paper, then it makes more sense to write that generic statement at the top. Okay, but if you're only doing a thing once, it's perfectly acceptable to write the names of the actual data points that were subjected to statistical tests in the methodology. Right. So that was tests of comparison. Okay. What about tests of association? These are your classic categorical variables. And you're going to report in your methods that you used Fisher's exact test or chi-square test. So again, I've put this up. They have to mean something to you. You need not know all the intricate details, but you need to have this mental picture. Fisher's exact test, that's a 2-by-2 table to see if the numbers are evenly distributed. In other words, for example, in health science, there are 20 male professors and 5 female professors. That's 4-to-1. In law, there are 40 male professors and 50 female professors. That's now 4-to-5. Is that a random spread of numbers, or is law actually promoting more females to professorships than health science? Right. You've got a clear idea that's a 2-by-2 table, and that lends itself to Fisher's exact test. And you know that we use the chi-squared test for when we have more than a 2-by-2 table. For example, here I've also thrown in the results for professors in engineering. So if you write in your methods that you did Fisher's test, but it was on data that consisted of 3 faculties and 2 genders, well, then again, you're giving away your lack of literacy in how your results were analyzed. Fisher's test can only be done on 2-by-2 tables. Chi-squared can be done on anything, including 2-by-2 tables, but because Fisher's exact test is a little more accurate under certain circumstances, we normally just use that. These hormones, our cortisol and adrenaline, have diurnal rhythms. So you have to state your methods in sufficient detail that somebody can have a look and say whether they believe it or not, or say this is actually not correct. So, as you know, we talk about who or what we studied. We studied male rats, or we studied patients admitted to, of course, the Alberto Central Hospital. What you did, we injected them with adrenaline and measured their cortisol, or we observed their progress after 6 months, whatever it may be. how you handle the results, okay? Results were taken and stored on a spreadsheet and blah, blah, blah. But then very importantly, how you analyzed the results. Because this is the point where you and an independent reviewer of your data may part ways. That reviewer may say, I agree fully with who or what they studied. Good study. I agree fully with what they did. Good study. I agree fully with how they handled the results. But I cannot agree with the statistical handling. I do not believe that a t-test was appropriate. A Mann-Whitney U-test would have been more appropriate. And when I do that, sadly, I no longer find significance. So now you cannot allow anybody to do that if you don't provide the information on how you handled your stats. So again, it's a critical part of the scientific method is reporting all your methods, including how you analyzed your data. And it's not, again, some sort of mysterious religious formula that's dropped in to look good. Let's change this to reporting p-values now. I'm going to start off with bad statements and then work up to better ones. This used to be very common. The mean cortisol concentration was significantly higher in males than females, p less than 0.05. No, say the medical journal editors. Okay, we no longer want less thans, we want actual values, p equals 0.02, with one exception. That's if it's less than 0.001, then you put p less than 0.001, and you don't put p equals 0.00046. Nor do you say p less than 0.0000001. The decision has been taken, 0.001 is as far as we go, and everything below that is less. Right, so keep the editors happy, the full p-value. But those editors are still not happy. They do not want us quoting p-values in the absence of any numbers or data to actually contextualize that. At least in males, it was 135, in females, 113. Now we've got some idea of the sort of scale of the difference. P equals 0.02. So our journal editors are just a little bit happier, still not completely happy. What they would like to see is that the mean is accompanied by a 95% confidence interval. Okay, that tells you how close to the real mean you believe the mean that you have calculated actually is. It's unlikely to be less than 129 or more than 141 for females, less than 98 or more than 128 for females. And that equates to a p-value of 0.02. So really, you should be stating your results like that. And then to keep them completely happy, you would actually have to add one more thing in, and that's the group size in each case. N equals 35 or N equals 42. Right. So in summary, p-values must be fully supported by summarized data. Means, confidence intervals, sample size, and not just the p-value. Right. So this is a direct quote from their instructions. Do not quote p-values in isolation without quoting the result. Quote the p-value, the sample size, the measure of precision, which is the 95% confidence interval, and in some cases, effect size. So you see, that statement is really not good enough. Out it goes. We should have been writing something like this. Now, there are different ways of setting it out. One of the problems is, I find, because we use those parentheses for the confidence intervals, it becomes very difficult if we would have liked to put the whole thing in parentheses. Males brackets, mean so-and-so, standard deviation so-and-so, because then you end up with brackets inside brackets, parentheses inside square brackets, and it all gets very confusing. I actually spent this morning, part of this morning, trying to find out what is actually recommended. I couldn't find anything on the biomedical literature. The American Psychology Association, which is really the experts in many writing styles in science, say do not put brackets inside brackets, rather delineate things clearly with commas, which is something I might have tried somewhere or other, but it is just a little bit confusing. But whatever you do, make sure it's absolutely clear what each number is and what it refers to. With my own students, I've come across statements like this where I've actually had to say, but I'm sorry, is the 7 or the 78.6, okay, the control or the patients? It's not at all clear to me. So make it absolutely clear that the meaning cannot be confused. Right. So why do they want all of this? If we give the means, you give some idea of how far apart the results are. You also give some idea of your confidence in the mean that you've calculated, which tells you far more than just saying p equals 0.02. So that's why they want it. And sample size influences likelihood of finding significance. If, for example, your p-value was not significant, your reviewer or marker might say, that still does not negate their hypothesis. That's a very small sample size. I suspect that with a larger sample size, that p might become significant. They couldn't say that if you didn't quote the sample sizes. And the second thing is, very often, a particular test may not include all the subjects. So you might state that you studied 120 patients with rheumatoid arthritis, but it's very likely that on the day when you put them on a treadmill to see how far they could run, only 85 of them turned up, okay? The other 35 were sick that day or got the day wrong or didn't feel like coming or whatever it is. So though you said that you recruited 120 patients in your subjects and methods, it may very well be that for this particular test, N was 85 and not 120. So you've got to state that so people know the actual number involved in that comparison and not just the overall total number of patients that were studied. Right. Next thing, the statistical packages give you p-values to like 8 places or something, right? Those journal editors have decided, no thanks, they don't want that. Anything less than 0.001 gets written as p less than 0.001. Okay. Anything between that and 0.01, you quote the 3 figures. P equals 0.003, not P equals 0.002567. Okay. Anything above 0.01, you just use the 2 figures. P equals 0.04, 0.05, 0.09, and not 0.04955. And if it's above 0.1, then you can use 2 figures again, 0.38, 0.64, 0.99, whatever it may be. Okay, so the numbers are rounded off, and we don't quote p-values to extraordinary numbers of decimal places. Similarly with rounding off numerical values, and I find this is often very poorly done when people share their results with me. We're going to go through examples again and show how they should be improved. The mean age of the patients was 45.125 years, and of the controls was 40.356 years. If you use Excel, it's perfectly capable of giving you means to 3, 4, 5, 6, 7, 8 decimal places. But how many are you actually going to put in your paper? Right. The rule is simple. Firstly, you must not claim a precision that was not really possible. If you say 45.125, you're actually suggesting that you could tell the difference between a patient aged 45.125 years and 45.126 years. That's a false precision. You didn't do that. You asked them to say whether they were 44 or 45 or 46. They weren't asked for their age to 3 decimal places. So it's actually scientifically wrong to put all those decimal places there, because the actual data on which that's based was not that accurately obtained. And then the second point is, it's also incredibly more difficult, for your reader to make sense. Remember we talked, I've talked some time back about information overload and the limits of the working memory. Well, there's no way the working memory can make sense of all those digits. The next line is so much easier. 45.1 years and 40.4 years. The editors go so far as to say, well, what about 45 and 40? If I tell you that the age was 45.1 and 40.4, and the difference is significant, have I really provided you with useful additional information instead of saying that the mean age was 45 for the patients and 40 for the controls, and the difference was significant? And the answer is no, I haven't really. Okay, so you need to use your brain in terms of deciding how many significant places or decimals, whatever it is, to put in. There's no magic formula, and it's not more scientific to put 2 decimal places or 3 decimal places. In fact, the opposite. The scientific method is to say, I cannot state my result more precisely than 1 decimal place, and therefore I will not state my number more precisely than 1 decimal place. The other is scientifically illiterate. So I sum that up as numbers should be rounded sensibly. In other words, you've got to think about what you are doing in order to decide how to write them. Now, what's wrong with this statement? It's inconsistent. One has got 3 decimal places and the other one has only got 1. Okay? They must be consistent. So if you want to use 3 decimal places in one, then you must use 3 decimal places in all of them. But I think we'd all agree that the 3 decimal places is entirely inappropriate for a hemoglobin concentration anyway. And we almost always use 1 decimal place. Okay, 74 grams per liter. Okay, 77.4 grams per 100 ml. You can even argue about the 1 decimal place, but we won't go into that now. All right, but the point is there should be the same convention for both of them. Numbers should be rounded consistently. Right, so we don't like that. But what if you tell me, no, but actually, Prof, it really was 116.3. It was 116.300. The answer is to be consistent, and you must actually write that. Okay. Sorry, repeated myself there. So I'm not sure, got out of sync there, but then it should really be written as 116.300 to show you that it was rounded to 3 decimal places. Right. Okay. Similarly, what's wrong here? 1 decimal place with a mean, and suddenly you've got 3 decimal places for the standard deviation. And in fact, the next standard deviation, we've only gone for 2 decimal places. Again, you must be consistent. There should be the same number of decimal places in general for the standard deviation as for the mean. Be consistent across all representations. I've done that there. 81.3, standard deviation 55.8. 116.3, standard deviation 48.2. There are exceptions. Okay. The mean age of the patients was 45.2, standard deviation 7.3, 1 decimal place. range 31 to 60, no decimal places. That's in fact not wrong. The reason is that people's ages may have been recorded to the nearest year. But in general, when you amalgamate a lot of data points and do a calculation like an average or a mean or a median on them, it actually comes out as more precise than the basic data. So in fact, in this case, quoting the mean to 1 decimal place with the original data was to no decimal places does in fact make sense. That's a little bit of numeric literacy. Percentages. No, say the editor, we don't like that statement. We found that 30% of patients were discharged alive. Always quote the numerators and denominators. We found that 15 of 45 patients, 30%, were discharged alive. And throughout your tables, you should quote the numbers as well as the percentages, okay, and not just the percentages. So you always give the base numbers on which the percentages were measured. And similarly, you should really give the confidence intervals as well. And if you do the appropriate statistical tests of your 30%, you may get a bit of a shock and find that the confidence interval for your 30% is all the way from 19% up to 41%, which is rather a large range. So we should be giving confidence intervals as well as our percentages. Right. That's almost all. But here's one thing we don't have to say. As you well know now, if you do a t-test, your stats software will throw out the t value at you. If you do ANOVA, it will throw out an F value. If you do a chi-square or a Fisher's exact test, it throws out a chi-square value. If you do a Mann-Whitney U-test, it throws out a U value. You do not have to quote those intermediate parameters in your results. So we could take out the t equals 16.22. Okay, those intermediate values like t and u and f and z and chi-squared are not reported. Okay, however, certain tests produce a wide range of statistical outcome parameters beyond the p-wave, the p-value, and they have to be included. Don't let this confuse you, but the point is this is a multiple regression, and the editors want a beta value for each variable in the multiple regression. That's its coefficient when you draw a straight line. Okay, and the p-value. And then overall, they want the r-squared value, which gives you some idea of how tightly the equation, the parameter, the model you've come up with actually fits and explains the data. As I said there, beta and r-squared are values returned by a multiple regression, which are themselves interpretable, have meaning to the reader, and the journal editors would like them. But nobody expects you to remember any of this. But when you come to write these things up, as I've had to do recently when I was writing this up with my student, okay, we had to go and do a bit of a Google search to find out exactly how it's recommended that a multiple regression is reported. Right. 2 conclusions, 2 slides left. 1, accurate descriptions of the methods that you used are important. And I used the example. You quote your results. You found the p equals 0.044. It's significant. You drew conclusions. You then share your data with somebody else who gets p equals 0.06. And now it says it's not significant. What's the problem? You used a student t-test. They used a Mann-Whitney U-test. And seeing you didn't say in your methods how you had done the analysis, they are unable to reproduce your results. Right. So my second point, again, as I've made repeatedly, you have to, sorry, bad grammar there, you have to possess a basic degree of numeric and statistical literacy. if you are going to write up numeric results and describe what you did with them in your methods. You don't have to be a hotshot statistician, but you've got to have some idea of what is done when. You've got to thoroughly understand the statements you wrote in your methods, okay? And you cannot afford to come up with some mishmash, which shows that you don't actually understand yourself what has been done with your results. Thanks, and that's all I've got to say.
Gosh, I had a couple of aha moments. I'm sure everybody else too. Some other things that I didn't see as clearly, I now see clearly. Let's open the floor to some comments or questions. You can just unmute and talk. We're not such a big group that you have to formally put up a hand.
Hi, Richard. Thank you for that wonderful presentation. It's Naina.
Yes.
Yeah, I can't tell you how I was trying to unscramble my brain, trying to recall all the stuff I did in Psych 3. So thank you for that. And but I think the most important message that you are giving is the attention to detail in methodology, which is generally overlooked. And I can tell you as an editor of a qualitative journal and a reviewer, that seems to be the case for qualitative studies. It's almost like just ignore it. But I think what students have to understand is you are producing knowledge, and we need to know how that knowledge was produced. And that's where the reliability and validity really plays itself out for the reviewer to assess how could I say, whether your research is worthy of being published. So thank you for that. I really must say I enjoyed it, even though I was lost at many points, but I'm going to unscramble my brain for sure.
Right. I did apologize and say it can be very dry and it could leave a lot of people behind, but it's just making the point again that there is sense behind it. There is a right approach and a wrong approach. Not necessarily one right way, but there's a right approach which we need to have. I can only agree with you, about the casual way in which many of our students approach the method section of their papers. And the sad thing is I have read examiners' reports, failed theses, which did not even discuss the results. They just said, it is not clear to me from the methods that the student has understood exactly what they're doing or what the difference is between this and that. And therefore, I have no confidence in their results. Full stop. That's all they said. That's enough to fail the thesis. So you could actually fail on your method section without your examiner even reading one page of your results. That's how critical it is. It's the old, garbage in, garbage out. If your analysis you did of your data is garbage, then your conclusions are going to be garbage as well. As simple as that. I have to say too, by the way, and what you say, that the psychologists are much more critical and much more diligent about how they report statistical tests and things. Far more so, in actual fact, than the biomedical journals.
If I can give any advice, it's to take things, baby steps for yourself. Like I've been trying to design, and I'll get to it soon, a page where students will put down what the variables are that they are measuring, and then look at whether they are categorical or not. Or is the distribution normal? So they'll be able to make up little bulleted baby sentences like, I am comparing two normal distributions. They are height and weight. And just to get things clear in their own heads. Obviously, by the time you report that in your paper, it's different. But you will know why you're using a certain test if you talk to yourself like that in short sentences and make it, just clarify it. And those are the PhDs that will pass, those that have written it. Sometimes it can be as staccato as that in your introduction to a paper, or somewhere in your thesis where you're explaining things at the really basic level. Are there any other comments from students about presenting your work for review or examination?
I would
yes, Prof.
add one comment,
Yes,
if I may
Prof.
now, because it's so important, Colleen, what you've just said. Nor can you afford to wait till you've got your results to decide what you're going to do with them. You've got to have a very clear idea when you design your study and draw up your protocol, what sort of results you're going to get and what you are going to do with them. You've got to have a clear idea that I have two groups. One is treated, one in controls. I will measure the means, and therefore I'm going to use a t-test. Don't wait till you've done your study and then wait for somebody else to tell you what it is you're actually trying to compare with what. And I've seen some very unfortunate cases of that. The bottom line is they amassed a whole lot of data, but it meant nothing because they'd never had a clear idea of what the data they were amassing was going to be used for. Anyway, sorry to interrupt. Somebody was about to say something.
I think there were a few people who wanted to talk at once. And Abraham, you've got your hand up. So if anybody else wants to talk, just put your hand up and then I'll ask you to speak in order. So Abraham, please go ahead.
Thank you, Professor, for your presentation. I'm really delighted with your kindly presentation. One thing I want to ask you that specifically on the, while we are justifying on the declaring as significant test, for which variable type, like categorical, continuous variables, which type of the tests are used to just declare beyond the p-values, specifically for different studies, we'll use it. Have you got my question?
No, sorry, I'm actually not too sure what the question is.
Hello? Yes.
Hello, sorry, I didn't quite actually understand the question. Maybe I missed it.
My question is, while we are justifying, like on the model fitness test, while we are justifying once for like continuous variables and for categorical variables, for which type of variables we will use a specific type of model fitness tests, or we will use only p-values?
Okay, well, depending on what your data are, categorical, continuous, depending whether they're skewed or normally distributed, depending how many groups you've got, et cetera, this goes on and on. So you will be pointed to use one type of test or another test or another test or another test. And in general, all of those tests return p-values because they're telling you what are the possibility that results that look like this could be thrown up by chance, okay? And some of them will have additional important values that go with them, such as the correlations having an R value, which gives you some idea of just how strong the association is. So the answer to that is one has to understand a little bit about statistics in order to understand my answer to the question. And certainly, early next year, I'll be doing the stats course again. And those who haven't done it, I really do recommend that you do it. It's not so much designed so that you can go and do your own stats. We all know that a little bit of knowledge is dangerous. But you should at least have some pretty confident idea about when a t-test is done, when an ANOVA is done, what an R value is, and so on and so on. Thank you.
Wanda, would you like to unmute and ask your question?
Yes, Prof. Thank you very much for this presentation. I somehow wish that it came before I actually wrote our previous paper, which is submitted. One thing I learned from this paper that I submitted, and there was a lot of values in it, is that it often helps to look at what you're doing and go through the literature and see if anybody else did similar studies and see how they reported. I think that's how we got to navigate through it. And it's really, you'll be surprised how much information you're going to get from there. It's a good habit. The other thing is get your target journal and see how they want to report, because some want you to report to 3 significant figures, some to 1 decimal place, some to 2 decimal places, and look at their reporting style. And because what would happen is you do this whole write-up and you've targeted the journal, and then you'll have to sort of redo everything. Maybe you are doing like 2 significant figures and then they want 3 significant figures. So before you do your write-up, there are these little details that you ought to go through, and it does help. Thank you very much, Prof. It was a wonderful presentation. Thanks.
Thanks, Stefan. I'm glad you brought that up. I meant to mention it and should have. These journal editors may have come to some broad rules, but there are little points on which journals often vary. You know, in the same way, some like a Vancouver system with a little number superscript, others like a number in round brackets, others like a number in square brackets, and so on and so on. The same thing does apply here. Some like big P for a p-value, others like a little p, and so on. As you said, some may want a different number of significant figures. So having got the broad principles of what I talked about, you're actually quite right. When you submit to a particular journal, you have to go through their instructions to authors very carefully. Right, but the major point still is, it's no problem if the journal accepts your paper and then the so-called copy editor says, please change this to a capital and please put a comma here and please put square brackets instead of round brackets. No, that's no train smash. What you don't want is the editor or your examiner throwing the whole thing out because it makes no sense. There's clearly no understanding behind whatever you've done. That's the dangerous thing. Yeah. Putting a round bracket instead of a square bracket, that's just convention, and that's got nothing to do with understanding. You really, no sensible examiner will fail you for putting round brackets instead of square brackets. But they will fail you if you don't actually understand what it is that you're putting inside those brackets. Okay.
I'm just going to add a comment there. In this last week, I've had a student submit to a specific journal and it was rejected outright because of style. And she resubmitted with about half an hour's work on having read the style requirements and then doing it to the style that the editor wanted. So had she given the attention, like Lavunda said earlier, then she wouldn't have had to go through that. But that has never happened to me before. It's the first time it's ever happened. Marianne, would you like to unmute and ask your question?
Thanks, Colleen. Richard, it's quite a simple question, I think. Yeah. I see you put a note before your decimal in the with the p-value, and some approaches just have the decimal. Which is the more accepted format now?
A decimal without a note in front.
Yeah.
I don't think I've ever seen that.
I've never seen that either.
Mathematical sense.
Yeah. Oh, really? Okay, I have. All right, so I was just checking. Okay, no, that's fine. And then I was interested that the p-values, maybe it's a while ago since I did stats, but we always told the p-value had to be reported to 3 decimal places. So it's acceptable to report the p to 2 decimal places.
If it's between more than 0.001, okay, more than 0.01, then 0.02, 0.03 is wanted, not 0.021 or 0.03. That again is just convention, and that's what's now preferred by that committee of medical journal editors. Okay, no doubt there are some journals that will still stick to some other system. Right.
Thank you so much.
Again, the main point I'm making is that there are sort of rules, and try to follow them and don't just make it up for yourself as you go along. Particularly make it up inconsistently, sometimes 2 decimal places and sometimes 4 and sometimes 5.
Right. Thank you.
I don't see more hands, so I'm just going to go to the chat There is one. Oh, Elliot. Elliot is a hand up. Please ask your question.
In fact, I'm not asking a question. I just want to say thank you so much, Prof, for such a very informative presentation. That's all.
Thank you.
I'm sure it's a pleasure for Prof Heft as well. or these talks, we both get quite a lot of pleasure out of them. And I learn a lot from Prof Heft too. There's a question in the chat here, Richard. I think we have discussed this before about our courses and making recordings available of the courses. I think it's generally been accepted that those are not going to be available, but these talks do become available on the website. I don't know if you want to comment on that.
Okay. No, my last statistics course, I was actually a very good boy, and for once, and I managed to remember to record it. And I have done a bit of subsequent editing and turned it into, well, a Zoom type MP4 presentations. So it is available in a closed Dropbox. So I just have to let anybody who wants it to know what the password is. I'd love to make it freely available on the university website. Colin, you can comment on that. I think the understanding is ICS sent you away with a flea in your ear and said they didn't have space on their server for these very large presentations, which I think is very unfortunate.
Yeah. It's a Prashini. If you just email Prof Heft, he'll give you the password for you to access that. Good, thank you.
No, I'm paying a certain amount of money every year to Dropbox to get more storage space, and I'm using my paid-for Dropbox to distribute this university stuff.
Yeah, I think maybe, Richard, we should have another meeting with people just to try and talk about the sense of it. I see another message has come. Okay. Right, next week, Dr. Veena Singaram will be talking to us about the examination process. So that would be, for those of you who are about to hand in, it's a pretty good idea to get an idea of what examiners look for. So thank you, everybody. We'll see you next week, the same time, same place. Thank you very much. Bye-bye all.
Bye.
Bye-bye. Bye.
Bye.